This is the introduction to our FM laboratory. The key component in FM signal generation is the VCO or VTO, voltage controlled or voltage tuned oscillator. The way the VCO VTO works is that we input a modulation voltage and the output is a variable frequency signal, which is an FM signal. Now the typical Vco Vto transfer function looks like this. We have an input voltage on the horizontal axis and an output frequency on the vertical axis. Now at 0 volts input, the oscillator will function at what is called a rest frequency. So the oscillator is always producing a signal. Now if we change the input signal with a voltage, we will change the output frequency. Now assuming the VCO transfer function is linear, if we input a voltage V1, we will produce an output voltage FH. In this case, a higher frequency signal than the original rest frequency. Also, if we input a minus V1 signal voltage, we would produce an FL frequency. So we have a variable frequency oscillator. This is the heart of FM signal generation. There are several basic waveforms to look at. Typically a square wave input would produce two different frequencies associated with one voltage and the second voltage. And then we will of course go to a sinusoidal input, which will be the typical FM signal that we are used to modulating a RF carrier with. The RF carrier will typically be the rest frequency. So if we're talking about a channel like 98.7 megahertz in FM, that would be the rest frequency. The signal out of the VCO will be our FM signal, and this is its components. We have A cosine 2 pi fc of t plus m sub f sine 2 pi fm of t. So we have a few new terms to look at in terms of the FM signal compared to the AM signal. So the new terms are: A is the carrier amplitude. It will be constant in FM. F sub c will be the carrier frequency. You can think of that as the VCO rest frequency. The modulation index, m sub f, similar to MA in AM, but operates quite differently. And finally, the modulation information frequency, which was similar to what we had in AM. So we have two signals that are determining the actual frequency of the transmitted signal. Both the carrier term and this term here related to the modulation. If we look on the diagram of the VCO, we can see that the change in the carrier frequency must be related to the change in the voltage input. Because the frequency out of the VCO or the FM signal must be related to the slope of the line, we know that the slope is the change in frequency over the change in voltage. This is given the term K sub O, which is the VCO sensitivity constant. The actual frequency will be determined by the m sub f sine 2 pi f sub m of t. So this voltage will produce the carrier frequency change, m sub f value. So the modulation index, which determines the change in the frequency of the carrier, will be related to delta fc peak divided by f sub m. But delta fc peak is obviously related to the modulating voltage. And so the final relationship we have is the modulation voltage peak times the K sub O value produces the change in the carrier frequency divided by the m sub f value to give us the modulation index. The numerator of this equation is often called the deviation of the carrier, because the carrier will be changing frequencies from rest to a higher frequency and then down to a lower frequency. So the deviation is the deviation of the carrier. F rest to FH, F rest to FL. On the generator, you will see a button referred to as mod. We used it in the AM case. If we turn on modulation, select type and FM. In the FM selection, we have the FM frequency. That is the modulating frequency, F sub M, just like in AM. In this case, I have it set for 5 kilohertz. The shape is similar to AM. We can have sine, square, triangle, ramps, up and down, various. And the deviation. Remember, the deviation is the amount the carrier will change based upon that input voltage. In this case, I have it set to 100 kilohertz. So I have a sinusoidal modulating frequency and of 5 kilohertz. Now I'm going to change the modulating frequency to be a square wave, because this tends to be a simple one to display. If I do that and look at the frequency display, I see a variation in my FM signal. Now there's a few things to tell about this signal. One is the amplitude is the same all the time. That is the A value. It does not change in FM. Now my frequency is quite high at 5 kilohertz, so I can't really see the changing in frequency, but I can tell there is a change in frequency. So I'm going to go back to my generator and make it the change in frequency much slower. So I've changed my FM modulating signal to be 200 millihertz, which means it'll change every 5 seconds, 1 over 0.2. If I look, the shape is still square wave. If I look at my signal, I can see that every 5 seconds the frequency is changing. If I look down at the values, it is switching between 1.1 megahertz and 900 kilohertz. So that is the 100 kilohertz deviation term. 100 kilohertz above the carrier, which was 1 megahertz, and 100 kilohertz below. Just reminding ourselves that our original carrier was 1 megahertz. Now, if I look at this on the spectrum analyzer, I will see the changing in frequency. Now, I've set up my spectrum analyzer for a 0 to 2 megahertz span. So right in the middle is 1 megahertz. The square wave modulation is creating the change in frequency. We can change from the lower to the upper associated with the square wave. 900 kilohertz, 1.1 megahertz. Let me go and change the frequency to deviation to 200 kilohertz, 1 full division to the right or left of the original carrier. And of course, we see the carrier changing 1 full division or 200 kilohertz from its arrest frequency. If I turn off the modulation, we see that the carrier is at the rest frequency of 1 megahertz. Now, this very simple square wave modulation of the carrier actually was used in the early days as a frequency or data method called FSK, or frequency shift keying. We had something similar in AM called ASK, or amplitude shift keying. Now I'm going to change my shape of modulation to be sinusoidal, and we'll see a little different display. We see that the waveform is now smoothly going from upper frequency to a lower frequency. This is kind of like a slinky being compressed and then stretched, right? This slinky effect. Again, the amplitude is staying constant. Let's look at this on the spectrum analyzer. On the spectrum analyzer, as we expect, we see the frequency gently sweeping from 1.2 megahertz to 0.8 megahertz, the deviation value. Now in the frequency domain, we simply see the signal changing from one frequency to another frequency, and all frequencies between the upper and lower deviation are contained in there. But this is a very slowly modulated signal. We need to change it to something a little more typical, like related to our audio signal. So now I have changed the modulation frequency, f sub m, to be 5 kilohertz. If I look at this on the spectrum analyzer, I see a much different situation, because now we are changing from the higher to the lower frequency much quicker than the before. We're changing 5,000 times a second. If I span in to the unit and frequency, we can see that the FM spectrum is much more complex than the AM signal. So we have to go back and modify some signals. In the time domain, we can see this very fast change in frequency from the carrier to the higher frequency of 1.2 megahertz, then the lower frequency of 800 kilohertz. Looks like this in the time domain. To begin the spectrum measurements, first set up the generator for 1 megahertz and 0 dBm. Turn on the modulation, setting the modulation frequency to 10 kilohertz, shape to be sinusoid, and the deviation to be 2.5 kilohertz. In the spectrum display, switch to the linear mode, and we see the carrier and 2 sidebands. Record those values using the peak and next peak functions. Repeat measurements by changing the deviation value. If we want an m sub f of 1, that will be 10 kilohertz. We will see the spectrum change. If we change to the deviation to 24 kilohertz, we'll see a unique display where there is no carrier. You will need to zoom out, span, zoom out to be able to display all of the sidebands. Record the values, peak, next peak, and you can record the frequencies and the levels of the sidebands. Repeat those as designated in the handout.